Okay. So the optical property, actually, the optical property, the transition of electron from your ground state to excited state, when electron transited from ground state to excited state and then returns, various types of the various types of things, various types of matter occurs. These are the optical properties, and from that optical properties, we have prepared various instruments. Now, this is magnetic properties of material. That means if we place a material in presence of magnetic field, in the magnetic field, what will happen to that material? This is the magnetic property. Now, what can happen? The magnet can attract the material, or the magnet can repel the material, or the magnet do nothing to the material. The magnet can do nothing to the material. So if a magnet do nothing to a material, it is a non-magnetic material. But if it attracts or repels a material, then we call it magnetic material. We require every type of material, a non-magnetic material, a magnetic material. We require every type of material. Now, at first, we see some definition. What are the basic things? I think you know all. You have studied magnetic properties in your fourth year or third year. In transition metal, the magnetic properties of transition metal in fourth year or third year, you have studied?
Third year, sir.
Third year. Okay. You have studied the magnetic properties. Now, we will see the magnetic properties in slightly different form, in slightly physics-oriented magnetism. Now, how a magnetic field occurs? If you pass current through a coil, if you pass current through a coil like that, you will find a magnetic field from the coil. If you pass current through a coil or a solenoid, what do you mean by solenoid? Solenoid means cylindrical type of coil. A coil, this type of coil is solenoid. This type of coil is solenoid. If you pass current through this type of coil, then you will get magnetic field. And if you pass current through this way, you will get magnetic field to this direction. To this direction. The magnetic field is a vector property. Remind it. It has the value and direction. It has value and direction both. So the magnetic field H, we call the magnetic field H. H is equal to Ni divided by L. What is L? L is the number of the turn. Here you see, N is the number of turn. Here you see 1, 2, 3, 4, 5, 6 turns. So the N value here it is 6. It is 6. Now, what is I? I is the amount of current. I is the amount of current. And what is L? L is actually the length of this, turn from first turn to sixth turn. Sixth turn is known as your L. So the strength of the magnetic field that is produced by the current is depends upon the total number of turn and the amount of current and the length of the turn. It is the unit of this magnetic field is ampere turns per meter. Ampere turns per meter. Now, what is actually the magnetic field? We call the magnetic field, or we see the magnetic field as the lines of forces of the magnet. These are the lines of forces of the magnet. You see the lines of forces starts from North Pole towards it ends or enters in the South Pole. The lines of forces starts from the North Pole, and the direction of the lines of forces from the North Pole to the South Pole. North Pole to the South Pole. This is the lines of forces. So if the magnet is like this, then the lines of forces will be like this. The lines of forces will be like this. The lines of forces will be like this. And the magnet is, if it is a bar magnet, then the lines of forces will be like this. Now, if you place a magnetic material to these lines of forces, inside these lines of forces, if you place a magnetic material inside these lines of forces, then the material behaves like a magnet. If you place a magnetic material inside these lines of forces, then the material will behave like a magnet. And this is called magnetization of a material. This is called magnetization of a material. Now you see, this is a magnet. This is a magnet. How it is a magnet? You have induced current here, and there is a turning coil, so it became a magnet. Now it has lines of forces, and you have placed a magnetic material. This blue one is the magnetic material. You have placed a magnetic material inside this coil. So the lines of forces enters in this material. The lines of forces enters in this material, and this material becomes magnetic. So if this material becomes magnetic, it will have its own lines of forces. There are lines of forces of this original magnet, and now you have placed a magnet. You have placed a magnetic material inside this, and it becomes magnet. That means the magnetic material becomes magnet. So the magnet has own lines of forces, and it has also a flux density. What do you mean by flux density? Flux density means the the amount of lines of forces enters into this magnetic material. The number of lines of forces per unit area enters into this material is known as the flux density and is denoted by phi. So, due to this flux density, from this solenoid type of magnetic material, which have a value of h, it becomes, the magnetic material becomes magnetized, which have a value of b. So h is the value of the magnetic field of original magnet, and b is the value of magnetic field of your magnetic material, because your magnetic material became magnet now. So what is b? B represents the magnitude of internal field strength within a substance that is subjected to an H field. This, this material, this blue material is subjected to H field. From where H field comes? The H field comes from this red wire that is turned, that is turned, and in red wire there electricity is passed. So in any wire, any coil, in any coil, if you pass the electricity, it will become a magnet. So this, in this red coil, you have passed electricity, the red coil become a magnet, its field strength is H, then this H induced that that magnetic material to become a magnet, and after induction, the magnetic material becomes a magnet with magnetic field strength B. Now, the unit of H was ampere turns per meter. Ampere turns per meter. How it comes? I is the applied current. The unit of current is ampere. N is the number of turn in the coil. The number of turn is N. So ampere turn, upside ampere turn, and in the lower L, L divided by meter. L is the length, you know, the unit of length is meter. So from the definition of H, the unit of H is ampere turn per meter. But here in the magnetic material, there is no turn. So it has a unit of Tesla. It has a unit Tesla, or Webers per square meter. Webers per square meter. Now, both B and H are vector quantities. It depends on both the direction and the value. Both B and H are depends on the direction or uh, and values. Now, what are the difference between B and H? H is the original one, and B is the induced one. Both are magnetic field. Both are magnetic field, but H is the original one. Its unit is ampere turn per second per meter, but B is the induced one. It became magnet by the original one, and and its unit is Webers per square meter or Tesla or Tesla. Now, what is the relationship between B and H? What is the relationship between B and H? So, the relationship between B and H is the B is equal to mu H. Now, how this relationship comes? How this relationship comes? Say, let us suppose we draw a magnet. Say, for example, this is a magnet. This is a magnet. Shape fill, no fill. This is a magnet. Now, okay, if I turn it, say for example, this is a magnetic material, and these are the lines of forces. Say this is one line of force. These are the lines of forces of these are the lines of forces with field strength H. These are the lines of forces with strength, you see, H. Now, what will be the B? Due to application of H, this material, this magnetic material became a magnet. So it will have its own lines of forces. Say, for example, these are its own lines of forces. I can okay, this reds are its own lines of forces. Okay, okay. These reds are its own lines of forces, and you call it B. Okay, these are B. So inside the material, you'll see inside the material, the lines of forces are both H and B. Inside the material, the both H and B are in the same direction. Both H and B are in the same direction. But outside it, say for example, this is North Pole. This is North Pole. and this is South Pole. This is North Pole and this is South Pole. So this B, you see, these lines of forces will come from the North Pole, from this way to this way, will come from this way to this way. This line force uh, exits from the North Pole and enters in the South Pole. I have told you the lines of forces exits from the North Pole to the South Pole. So outside it, say for example, this H field, here is also H field, here is also H field, H field, here is also H field, here is also H field. So outside outside the material, this lines of forces of B of that material will oppose the H, but inside the material, this B will assist the H. Actually, if I can make a, if I see, no, it is not possible. Now, you can see these lines of forces will out from the North Pole to goes to the South Pole and enters from the South Pole. This from this and this also. This lines of forces will out from here and it goes to here. So you see, inside the material, this red one assists with the with the with the black one, but in outside this red one, this red, the arrow will be like this, the arrow will be like this. This red one will not assist to this magnetic lines of forces. It is opposite to this magnetic lines of forces. So what is mu? Mu. So here you see the field strength increases, and here you see the original field strength decreases. So mu is the mu, this B is equal to mu into H. So what is mu? Mu is that factor by which H is increases, or H will be increased, or H will be decreased. Mu is that factor by which H will be increased or H will be decreased. Here you see H increases here inside the magnetic material. H increases, and outside the material, magnetic material, H decreases by the presence of this magnetic material. So mu is the factor by which H will be increased in the magnetic material, or H will be decreased in the magnetic material, or vice versa. H will be decreased in the magnetic material, or H will be increased in the magnetic material. Whatever it may be, mu is the factor by which H decreases or increases inside the magnetic material or outside the magnetic material. So in presence of B, H may be increased or H may be decreased by a factor mu. So mu is called permeability of that magnetic material, and the unit is Webers per ampere meter or Henrys per meter. Mu is the permeability and the unit is Webers per meter or Henrys per meter. Now, in the vacuum, B naught is equal to mu naught H. So what is mu naught? Mu naught is the permeability in vacuum. Mu naught is the permeability in vacuum. So B naught is mu naught into H. So in vacuum, permeability is always constant. That is a constant value of mu. And it is not mu r, it is mu. Now, what is mu? Mu is the permeability. And if you divide mu by mu naught, that means the ratio of mu and mu naught is known as relative permeability. The ratio of mu and mu naught is known as relative permeability. Now, what will be the unit of relative permeability? What will be the unit of relative permeability?
Sir, unit থাকবে না মনে হয়।
হ্যাঁ, it is unitless. It is unitless because both have units Webers per ampere meter, so there will be no unit for relative permeability. So what is the physical significance of relative permeability? Relative permeability is a measure of the degree to which material to be magnetized, to what extent a material to be magnetized. The relative permeability will tell you to what extent you can magnetize a material, a magnetic material. So what do you mean by then magnetization? Magnetization is the magnetic flux per unit volume. What do you mean by magnetic flux? Magnetic flux means number of lines of forces. Strength of lines of forces. Strength of lines of forces means number of lines of forces enters into the magnetic material. You have a magnetic material. There are, say, for example, 10 number of lines of forces enters into the magnetic material per unit area. Per unit area means per unit volume means per meter square. Say, for example, per meter square of a magnetic material, you have you have entered 10 lines, 10 lines of forces. So that is called magnetization. How much of magnetic lines enters into your magnetic material per unit volume, of course, enters into the magnetic material. That is called magnetization. If the lines of forces are high, number of lines of forces are high, then the magnetization is high. Or if the number of lines of forces are small or low, then the magnetization is low. This magnetization is related to B by equation B is equal to mu naught H plus mu naught M. M is the magnetization. Mu naught, you know what is mu naught? Mu naught is the permeability at vacuum, and you know what is H. So the magnitude of M is proportional to the applied field. This magnetization is proportional to the applied field, is directly proportional to the applied field. You know that if the applied field is strong, so magnetization will also be strong. So M is directly proportional to H. So M is equal to chi M H. What is chi M? Chi M is a constant which is called magnetic susceptibility. Which is called magnetic susceptibility. It has no dimension. This chi M is related to the mu r by this equation. Chi M is equal to mu r minus 1. So what chi M shows us, what chi M tells us? Chi measures the material's response relative to a vacuum. Say, for example, B versus H, if it is a B versus H curve. In vacuum, this is the line, and if chi value is greater than 0, then the line will be here, and if the chi value is less than 0, the line will be here. Now how it tells the the material's response relative to vacuum? By this equation. If the mu value is less than 1, if the mu value is less than 1, then this value will be negative. This value will be negative. Then chi will be less than 0. And if the mu r value is greater than 1, if the mu r value is greater than 1, then chi m value is positive. That means chi m is greater than 0. Then the line will be this. Then the line will be this. So mu r value actually, mu r value tells us what will be the chi value. What will be the chi value? Mu r, what is mu r? Mu r is this mu by mu naught. What is mu naught? Mu naught is permeability in the vacuum, and mu is the permeability of that material. If this value is greater than 1, then chi will be greater than 1, greater than 0. And if this value is less than 1, that means if mu naught value is greater than mu value, then it will be less than 1, then chi value will be less than 0. Now, if chi value is less than 0, then the material's response will be negative. And if chi value is greater than 0, the material's response will be positive, which you call a diamagnetic or a paramagnetic. It depends on the value of chi. Actually, it depends on the value of mu. That means relative permeability. That means not relative permeability, that means permeability and permeability in vacuum. So these are some definitions. These are some definition which we have to know. What is magnetic susceptibility? What is permeability? And what is B and what is H? B is the magnetization of your material and H is the original one. Applied magnetic field. Applied strength of applied magnetic field is the H, and B is the strength of your strength of magnetic field of your own material, which you want to see. Okay, this up to today.